Good morning, good afternoon, good evening from live at VeeamOn in Las Vegas 2015. This presentation is on certificates. It's kind of my introductory piece that I do. As it shows in the subtitle, it's how I stopped worrying and learned to love the CSR. So about me, I'm Jim Millard. I'm an engineer with OneTech IT Solutions, and I've been a geek for all my life, but I've been working as one for 20 plus years. Got all kinds of industry certifications, but the key point to understand from this presentation is that I am not a math or an encryption expert. So that, hopefully, the takeaway on that is you don't have to be an encryption expert to be able to successfully utilize certificates. So we're going to run through some of the items here. I'm going to do an introduction to what certificates are and how we can stop thinking of them as this ugly black box that we're forced to use. I'm going to run through some tips and tricks for setting up a Windows certificate authority, which is, believe it or not, very simple to do if you follow the handful of rules I give. And then with a very VMware-oriented slant to it, I'm going to talk about the challenges of replacing certificates in some of the VMware products, starting from the easiest going through to some of the most annoying. And then, because I've actually got a little bit of a live audience here, I'll take Q&A if there's still time. So, why do we need certificates? They're essentially used to encrypt the traffic that we're sending between two endpoints, and the idea behind that is, well, I hope it's obvious. We don't want somebody snooping and looking into what we're sending. VMware products use it. Veeam uses it for the Cloud Connect, so it's good to have that. All of your major websites that do any sort of e-commerce, it all relies on SSL for security. When you go to Google or Office 365 to check your email, you're dealing with SSL security. So it's a good piece to understand and have some understanding or some knowledge about. As IT people, though, we end up having to implement this stuff, and that's where the challenge is. People tend to, at least the ones that I've talked to, kind of hate dealing with certificates. They find it challenging, and it is a little bit of witchcraft, black box kind of stuff. So the basis behind certificates is it's a way of doing digital encryption. So apparently is a key part to this. It has to do with fancy math that takes human readable text or whatever that binary information is and turns it into pseudo-random noise. And the reason why it's pseudo-random or the apparent noise is because we need to be able to reverse it and get back to our original capability or the original data. So some definitions that we'll be going through, if I use the phrases plain text or clear text, they're the same thing. It's the unencrypted data. Ciphertext is what we get from running the plain text through an enciphering algorithm. Cipher is the actual algorithm that's being used. There are dozens of them. Probably the ones that people are most commonly familiar with today are the AES encryption suites. And the differences between AES 128, 256, et cetera, is just key length. The key itself is, call it the password. It's the thing that is used to uniquify, for lack of a better way of putting it, the encryption algorithm so that what I put through with my key cannot be decrypted by somebody else without that same exact key. A hash is a more interesting cryptographic feature. It's another algorithm, and its purpose is to take a large blob of data and create essentially a thumbprint. And it's a cryptographic method as well that you can actually key a hash. The more common ones that are used, like MD5, SHA1, SHA256, those are all non-keyed so that anybody using that hash can generate the exact same identical thumbprint when starting with the same source data. The other thing that's interesting about the hashes is that there's this concept that if I have a very large amount of data and a small hash, how is that able to represent that uniquely? That there's this concept of a hash collision where two different pieces of source information actually end up resulting in the same exact hash. That's part of why we don't use MD5. If we can avoid it, we go for SHA1 or even better that, SHA256, because key length, blob size means that the hash is larger, less likely to have those, and less predictably able to generate something that's going to result in the same hash. So in a very grand scale of things, the hash function is intended that we start with some kind of user text. It goes through the function. I'm just going to represent that by an H function. And what we get out of it is that cryptographic thumbprint. We have the idea of a symmetric cipher. And that is, with one key, you take your unencrypted text, or whatever it is you're sending that's usable as it is, you run it through the cipher, and I'm going to use E for an encryption algorithm, and out comes junk. Well, that same exact key is used with the blob of noise with the exact same cipher, and you get the data back. The advantage for this is that it's really fast. And in fact, modern silicon today has these encryption algorithms baked right into it, and it's extremely fast, even though it's pretty complex math that actually makes it work. The obvious problem with using symmetric encryption is, how do we share keys? Well, I could encrypt the key and send it to you, but then how would you decrypt the key? Exactly. So there's got to be a better way of sharing those keys. Well, some really smart mathematicians figured out how to create an asymmetric cipher. The idea is that you've got a pair of keys that are unique to each other. One key is used for enciphering. Whatever this key enciphers, only this other key can decipher, and reversibly. If you're familiar with the term PKI, or public key encryption, or public key infrastructure, we've got the idea of a public key and a private key. There's actually nothing special about private versus public from an asymmetric standpoint. They're just labels. So you generate this pair, the key pair, and you arbitrarily choose, this is the one that I'm going to share, and this is the one I'm going to keep locked up in a safe. So don't ever let anybody say that it's an important distinction of which one is public and private, unless or until you actually share one of those. The idea, again, on the asymmetric cipher is that we take our plain text, run it through with key A, and we get noise. The only way we can turn that noise back into the original data is to use its partner or paired key. So for very easy reasons, we can share the public key side, whichever one of those two we decide is public, and you can encipher anything you want with that public key, and only the private key holder can decrypt that data. Flip it around, anything that I encipher with my private key can be publicly decrypted by anyone holding the public key. The challenge with using that for, signing a message is as simple as I write the message, I hash it, and then I use my private key to encipher it. Once it's out there as part of your message, somebody else can use their public key, hash it, and decipher the enciphered thumbprint, and when they match, you know that it's actually verified. There's a drawback for the public key, the private public key pairs, and that is it's very compute intensive, and it's not something you'd ever want to do for bulk encryption. You don't want that to be the basis of a communication channel. You don't want to use that as the basis for sending large blobs of data. It just takes too long. It's too compute intensive. The other challenge to that is, once I've got something that's purportedly part of a key pair, how do I know that the partner key to it is actually the valid key? Because the reality is anybody can go out there and create a key pair and say, okay, I'm Microsoft, here's my public key, trust everything that I send from you. So we've got the idea instead that we have these certificates, which combines both the idea of the signature for here's my public key and you can decipher it using this, but it's only encrypted by the private key holder. This is the idea behind the self-signed, is that we've got our two separate keys, one's the public, one's the private. We use our private to encipher the public key, and then you put the public key and its signed version. That gives you the ability to loop back. So in other words, the key that comes with the blob can then decipher it. There's actually, in a certificate, more data than just that key. There's some identifying features to it. In the case of SSL, things like DNS names, certificate chains will have pieces to it as well. So you're able to verify that certificate by hashing the key itself to create a new thumbprint, and then you can go through, you take the blob, decipher it using the public key, and then do a thumbprint. The thumbprint is already there, and they match. So the certificates end up being like an ID card. They're issued by somebody you trust. So the idea of a self-signed cert, you accept it because whoever created it, you're going to trust from the get-go. In public commerce, we tend to shy away from that. We want to rely on some of the root certificate authorities, VeriSign, DigiCert, some of those folks that generate these signed certificates. We've got a chain of trust established by trusting them to begin with. So the idea behind here is that we have a CSR that contains my public key, as well as some other information in it, and you send it off to your certificate authority. What they end up doing is they use their public or their private key to encipher what you send to them. And so their signature is separate from your public key information. What that allows you to do is then go back through these chains and validate that what they sent, what they signed is valid back to your original root certificate that you trust the signer of that root certificate. So a root certificate is used to create an intermediate signer. Intermediate signer is able to sign an end server. In the TLS handshake, TLS is transport layer security. It is an evolutionary child of the original SSL. Again, I'm not too deep in the weeds on this stuff, but I want to say that when we talk about SSL 3, we're talking about TLS 1. SSL 4 is TLS 1.1 or 1.2, something along those lines. But the idea behind it is a client asks for or initiates that secure connection request. It's responsible for validating the certificate. It actually decides what symmetric key it's going to use, and it actually sends that over the wire using the public key encryption. And so we're able to get this private connection using a symmetric key that makes it real fast to do, but we use the public key encryption in order to securely send it. So then we're back to where's our root of trust start? And today we've got a handful, well actually if you look at the trusted root certificates list in your average Windows machine, it's more than a handful. It could be on the order of 100, 150, depending on whether or not that's been cleaned at any time recently. In fact, there was a bit of hue and cry over Microsoft including the Chinese state government's certificate authorities. So you have to trust that root certificate. And there's, in a Windows environment, you've got two different kinds of certificate stores. One of them is built into the Windows OS itself, and some applications will maintain their own independent certificate store. Classic example of that is Firefox. It does not use the Windows Cert Store. So we've got the public CA, and we could use that inside all of our environments, but there's a challenge to it. Number one, you might have a CA that's not trusted by everyone. It's part of that list of 300 plus 300 plus trusted CAs out there that if it's not actually published to a given machine or device, you could have a challenge. I have been on projects where we've had no problem getting desktops to properly trust and create SSL change with like a VDI environment or a Zen desktop, Zen app kind of thing. But when you want to do it through an iPad, for instance, its root authorities don't include certain CAs, so you would end up having to import those. There's also an interesting piece where recently the CAs that are out there publicly will no longer sign certificates that include non-public domain names. And so that the URL I've got in here, the DigiCert internal names piece, that's about how the CA consortium decided as a group we will no longer sign certs with those after a certain date, and I believe that date's expired. I have had to do several engagements already to exchange internal certificates from having those internal domain names to now being the public side. So my rule of thumb is go ahead and use an internal CA where you can, but only use the publics where you must. The other disadvantage on the public side is even if you use the most commonly trusted CAs, you're not going to get your certificates signed for free. There is cost associated with it. That's where the internal CA becomes very valuable because all you're paying for at that point is, in the case of Windows, a Windows license, or in the case of Linux, you're rolling it on your own using the open source software, and you're really just talking about compute at that point. So I'm going to talk specifically about the Windows Certificate Authority, and the reason is twofold. The first is that it's very common to find Windows in a lot of enterprise environments. Even if you're working towards a Linux-only environment, chances are you probably have some Windows floating around somewhere. The other advantage to Windows is it does have the GUI-based tools, and unless you're in and working with the Certificate Authority all the time, the chances of you remembering command line commands, it's challenging. So you've got the discoverability aspect of working with a GUI. So one of the pieces that you want to plan is an actual architecture for it. Please do not go out, spin up a new Windows machine. God forbid you take an old Windows machine that's running server and just turn on the CA. What it will walk through for you on the next version can get you in hot water. There are rules in Windows that say that once you've set up the CA, you can't change that machine's name. If you've got a domain controller and you put the CA on it, you can't demote it unless you remove the CA. If you've got a standalone machine that you want to make a domain controller and it's also a CA, you can't change it until you remove the CA. So you want to plan, definitely want to plan. In Windows, we've got two different kinds. One of them is Enterprise, which means it's AD integrated, and the nice part about that is it takes care of automatically publishing out where all those certificates need to be for the trust aspects of it. And then there's the standalone. Back up one note there, the tiers, you have the idea of the root, that's where you have that self-signed certificate. At some point you have to trust a root, so you will want a root inside of your environment. Then we've got the idea of a validity period, which is if I want to have a 10-year certificate, well, the CA has to be able to sign for that amount of time, and that means that it has to be, in case of Windows, overridden a little bit. You have to decide whether you're worried about the frequency of change, because changing it's a pain in the backside, or you're worried about having a long-term cert that if there's a good example, if you've got it with a 120 or 1024-bit key and you've signed it with the SHA-1, and now we've got all kinds of information about how easy it is to crack through something with a 1024 key or using SHA-1, and you end up having to change everything to 2048 and SHA-256. So you might want to change between short-term, long-term. It's really something you need to discuss inside of your environment, what's going to work best for you. So when we look at Windows for their validity periods, you by default, your root CA will have a 5-year, and if you create an issuing CA that relies on that, it will by default be a 2-year, and then you can issue certificates that last for 2 years. What you will not ever be able to do is issue certificates that run longer than the validity period of the certificate that's actually owned by the CA, which is really interesting. If you've got, say, a 5-year cert on your CA and you're in the 4th year, you can't issue a 5-year cert. You can issue one that's going to last to the end of that certificate's time. So it'll expire on the same date and time. So I like to go through and revise those defaults and run them up to a much larger time frame. The idea is that they're painful enough in some environments to replace that I really don't want to do it during this particular part of my career. So again, we like Windows because most organizations already have Windows somewhere. When it's done correctly, it's actually very easy to use and maintain. Part of why I'm discussing this is that if you do it incorrectly, it can be a real pain in the neck to update, manage, and move along to the next phase. And to be very effective inside of a vSphere environment, you still need the command line tools. So the comments earlier about the Linux and the CA part, that's managing the CA itself. In the case of the systems that are actually using the certificate signed, that's where those command line tools really come into play. So the design that's currently common and preferred inside of Windows is to have 2 certificate authorities as a minimum. One of them is going to be what they call an offline standalone root. The idea is that it's not domain integrated in the literal sense. Don't join it to a domain. And once it's used to create the intermediate or the subordinate, you're actually able to turn it off. You can turn it off, you can use VeeamZip to stick it into its own backup file off and remove it from your environment. Only time you ever need to spin that thing up is when you need to create new intermediate CAs. Your issuing CA is the one that's going to be on all the time. So it relies on the root, but it is domain integrated, which takes care of not only device enrollment, but you get the ability to take care of Windows security to validate who's allowed to create certificates, things of that nature. It works very well. That offline root, you take its certificate, you publish it with a GPO, and it works very cleanly. So if you're going to do this, we install our standalone root. Again, not a domain member. The only thing you want to put on this is ADCS, the certificate services. And as I show in the screenshot, you also want to have the web enrollment. And it just gives you a nicer, cleaner GUI than having to remember the cert-serve command line. 2048-bit key length, and I specify SHA-1 here. You may prefer to do SHA-256, and that is actually recommended by anybody that's setting up a new CA. The reason why you might stick with SHA-1 is if you have devices in your environment that cannot use the 256 thumbprint algorithm. Set your common name. Windows will want to use the name of the host without doing the FQDN, and it'll put an underscore CA in. So it's not actually based on the FQDN. I recommend you replace that. Change your expiration period. That's at the time that you're setting it up. I'm throwing in 50 years for the giggles of it. The cert-util command, this is where command line does come in for setting it up. We're going to override one of the flags in the registry to tell it we can actually use subject alt names. And that's the idea that a single certificate can correctly respond to multiple FQDNs. And the main use for that in a Windows environment is to do the short name in addition to the FQDN, which you're not going to be allowed to use if you're using a public CA. So again, these are to have multiple host names inside the cert, and the public side is commonly used with UC and Exchange. There's additional pieces here for some command line to take care of your validity period. The other way that you can do these periods is to go in and literally edit registry entries under the system control set services, and you find your CA in there. But you do have to restart the service in order to take advantage of that. Once you've done that, and I've actually found that it does depend on which version of the CA that you're using. With 2012, you can use that CA certificate for HTTPS, so that's not necessary. This is outdated unless you're using 2008, in which case you will need to issue yourself an SSL cert. GPO for publishing that offline root. You just create under public key policies under the security settings for the computer. Your subordinate, join it to the domain. Don't do any other roles to it. Again, certificate authority and the web enrollment. You're going to set your cert properties. Again, choose SHA-1 if you have devices that you know will not support it. If you have devices that you're sure you're going to be able to do 256, that is actually preferred today. And again, 2048 is preferred as well. Override the common name. You're going to end up creating a CSR. You're going to end up turning it around and using your root that you still have online and getting a certificate signed by it. You import your root certificate. You want to disable revocation checking unless you also want to go to the hassle of changing the revocation, the CRL locations in your root certificate, changing the lifetime of it, and occasionally bringing that root certificate server back online to regenerate the CRL. I find that to be quite a pain in the neck, so I tend to not do it. We change our lifetime, so we've got longer life that issuing cert can do, and we need to, again, make it capable of doing the SANs and get the thing started back up. Inside of an enterprise, you have to create templates. There is no way to just do an arbitrary CSR. You have to have it match I like to create the one for VMware because it's pretty much great utility on any SSL case for the web signing, but it's got additional functionality for the types of encryption that you can do in VMware. Again, the knowledge base article 206.2108 explains what the requirements are for that, and then you can create your SSL enrollment. Long-term web cert, it's just pretty straightforward. The key piece that you want to take away, aside from the time, you want that private key to be exportable. There are certain types of applications that either you want the same certificate on multiple servers, but you also need to have that private key available. If you don't make it exportable, it's kind of hard to move it around from host to host. Again, specific details on the VMware certificate template. Being able to do things like client authentication, the digital signatures, pieces like that are all factored into this. So here comes the fun part, the part that nobody likes, and VMware is actually addressed pretty nicely in vSphere 6, but I have not seen enough adoption of vSphere 6. I'm personally not up to speed on how we take care of the replacement of the self-signed cert in PSC so that we can use it with this, but that's where we want to go ultimately. So if you're inside of 5.5 and earlier, you're dealing with, say, a view environment as well, it's, well, as I put in here, it's kind of a certificate circus. A Windows platform, vCenter 5.5 has like 7 certificates that have to be replaced if you're going to switch from the self-signed VMware certs to your own CA. So a lot of challenges in there. This is our list of all the different certificates that you would have to change based on which version of vCenter, both between Windows platform as well as the Linux VCSA platform. As you can see, it's kind of a mess. So in order to change these for VMware, you are recommended highly to get the VCCAT. That's their script-based certificate automation tool. It does a nice job of creating CSRs, doing requests to CAs, binding them together with your your authority chains, as well as actually doing the replacements and resignaturing things. You'll need the local copy of OpenSSL 0.9.8. For newer versions of VMware, some of those may have changed. So again, you'll want to go back to the knowledge base articles for the specific version of vCenter, View, whatever the product is, and find out which version of the libraries are being used for the SSL encryption for that particular product. For Windows-based administrators, you're going to want to go to Shining Light to pull down their various copies. They have 64-bit and 32-bit. Make sure you get the right version for your platform. You can use the 32-bit tools on a 64-bit Windows. It's just not as efficient. Another product that's out there that it's going to be interesting to see what happens with VSS Labs. They were acquired by VMware, and so I'm not sure that we can even get vCert Manager anymore, but you can find things written about it. So depending on the version of vCenter you're running, there are different versions of the VCCAT. Knowledge base articles on where to download those are included here. This is where you have to decide for a given product, do I use a public or a private certificate authority? And again, it goes back to that idea that you use the CA internally if you can, use the public where you must. So good examples of the public is if you've got anything internet facing, like your View connection servers that go through security server, if you've got mobile device access, that sort of thing. So the easiest certificates to change inside of the VMware environment are the View connection/security servers because it relies on the cert store in Windows. Now, it doesn't actually use the certs in the cert store. What it does is it copies them to its own internal location for referring to them. But it's really pretty straightforward. You go into that cert store and you find the self-sign that was there when you installed it. You install a separate one. You change that original one. You'll see in there that it has a friendly name that is VDM. You remove that from the original, you put VDM into your new one, and then you restart your connection server or your security server service, and that's done. It's the best way. Composer's got a little more work to it. It can use the certificate store inside of Windows to kind of be the source, but there are more tools that you have to use to actually pull it down. It does not have that automatic capability of when you start the service, it automatically pulls it in. You have to go through and use this SVI config command. But on the grand scheme of things, it's actually a pretty easy way to take care of changing out that certificate. vCloud Director, sunset, but it's also one of these pretty easy ones that as long as you build the Java key store, you can very quickly get that certificate changed out. Certificate chains inside of all these VMware environments, you have to build them in a specific way. In Windows, each certificate is uniquely identified and lives in its own kind of bucket inside of the certificate store, whether it's a trusted root authority, a third-party root, intermediates, or the personal private keys. When we're dealing with these Java key stores, there is a specific order and fashion that you have to build them in, and when you do an export of a key chain out of Windows, it's not going to build them in this fashion. So this is where having some of those OpenSSL tools gives you the ability to burst that open, treat them as individual base64 blobs, and rearrange them using a notepad or other type of text editor. And so I've got here the list of what you would actually expect. You need to start with the most secure or most private, which is your private key, and then you would have its accompanying certificate, which ends up being the public-private key pair for our server. And then you would have intermediates in their chain order, followed by the root certificate as the very end. And as a final note, got in there, always use the base64 encoded. It's just, it works. So Windows only, you do this OpenSSL piece. It's handiest if you add that to the server path and then close the command shell, open it back up. Otherwise, you're either doing everything in that install location or you're forever having to make sure you've got the full path when you try and run the OpenSSL tool. VCCat, there's a little bit of prep stuff to it. My next to the last piece where the backup and snapshot when it's a VM is absolutely critical. I have done several of these where we're on the 4th or 5th certificate and all of a sudden it goes sideways and there's no way to fix it. It's in a broken state at that point, and reverting to that snapshot saves the day. ESXi is actually one of the easier ones as well. It's time consuming though because it's one Z at a time. There is no centralized way of changing the certs for a whole bunch of them at once. You have to have it in maintenance mode, you replace the certs, and then you bring it back out of maintenance. This all pretty much goes away when we move to vSphere 6 and the PSC. It takes care of replacing those certs to trust back to the platform services controller by default, so it's kind of nice. Some handy OpenSSL commands. You convert these bundles. The PFX is the type of bundle that you'll get when you export out of Windows. The .pem is just a handy, it's the PEM file format. It doesn't specifically need to be that, it's just what I use. I will throw out that final argument on there that looks like it reads nodes. It's not, it's no DES. There is an encryption that is done to the private key that if you put in the no DES, then it removes that as well. And I'll show you kind of what the difference is between the two. Actually, here's the piece to it. When you've got DES explodes these, and then you've got a PKCS1 looks different from a PKCS8 for the keys, and that's how you convert them. The decode the CSR, this gives you human readable information of what's actually in the CSR, the certificate request. Decoding the certificate, again, this is to give you information about what's in the cert. The Windows side of it, you would have a certificate, you double click, you get a nice GUI that has all that information about what's in the cert. That's what this X509 command does. SSL Shopper I found is a really nice resource for a lot of these commands that if they're ones that come up for converting or for decoding that I haven't listed but you would like to use, they've pretty much got the entire gamut of what's doable. And that's about it. So, any questions? I seem to have lost my local audience, but you got anything? I don't see any tweets coming out for it, so here we go.